now we'll state Green's theorem and we'll see some of the consequences. So the setup, suppose C is a simple closed curve that's the boundary of some region called R. And we'll let capital F be a vector field whose domain includes the whole region. So that's just saying it's defined everywhere on the region R. Then, on one side, we have a circulation integral of f along the curve C. Remember, a circulation integral is just a line integral that starts and ends at the same place. And this is equal to a double integral over the region R of the scalar curl. So the scalar curl is a scalar function, a real valued function. So on one hand, we've got a line integral that goes around a region. And on the other hand, we've got a double integral integrating a function over the whole region. So let's see an example. In this setup, C will be a counterclockwise circle centered at the origin with a radius of 2. And our vector field will be this mess. The prompt is to find the circulation of F around C. So we could do this using our setup for line integrals. We could parameterize the curve. We could plug it into this vector field. We could take the derivative and dot it with that to get us a single variable integral. And we could do it. It's a mess. I don't want to do it that way. We'll use Green's theorem instead, which says to find this circulation integral, we can find equivalently the double integral over the region R, that's the inside of the circle, not of the vector field, but of the scalar curl of the vector field. So we're taking our vector field and we're getting a new real valued function that's defined at every point. Kind of like when we take a derivative. So we can do it. We can find the scalar curl. We'll take the partial with respect to x of the second component. We'll subtract from that the partial with respect to y of the first component of f. Well, those partials are just 7 and 3. So we get 4. It's a constant. We can factor it out of the integral. And an integral over the region of just 1 is the area of that region. So the area of the circle with radius 2, 4 pi, multiply by that 4. 16 pi is our answer. Much easier than applying the original definition of a line integral. And the fundamental theorem of calculus for line integrals wouldn't help here. You can check why. So again, Green's theorem says we can take a circulation integral or find the answer to a circulation integral question by taking a double integral over a region. So hopefully that's easier. Not always. Sometimes Green's theorem works in the other direction. So 2 more points about Green's theorem here. First, we should think of this as a generalization of the fundamental theorem of calculus from our integral calc class. The second part of the FTC, on one hand, tells us to think about the boundary of a region. Well, in a single variable setting, a region is only an interval on the number line, and the boundary is the 2 endpoints. And on the other side, it has us integrating a derivative over that region. Right? We've got a function f. We can talk about its derivative, which is a new function we get at every point. Just like the scalar curl is a function defined at every point that we get from thinking about a vector field. And then one last application or observation is that Green's theorem shows us how the scalar curl sort of measures path dependence. So we know what it means for a vector field to be path independent, but we could ask, if that fails, how badly, how path dependent is it? So imagine we have 2 paths that go from a point P to a point Q. Now, in a path-independent vector field, the line integrals along either of these paths would be the same. That's what it means to be path-independent. But in a path-dependent vector field, we might ask, how different are these two line integrals? Well, to quantify their difference, we can take their difference, we'll subtract. And we'll do a little algebraic manipulation here. A negative integral we can find by reversing the bounds. So in Calc 2, this was just swapping the top and bottom bound. In this setting, it will be traveling along the path in the opposite direction. So if our path D goes from P to Q, minus D goes from Q to P. We can combine those. And then I want you to recognize if we were to travel along C from P to Q, and then along minus D, that is from Q back to P, then we've just traced a simple closed curve that is an oriented boundary for a region. Specifically for the region R. And so Green's theorem tells us the circulation around that boundary is the double integral of the scalar curl. And I realized this is maybe oriented in the wrong direction. We want our oriented path to be counterclockwise. So we can switch the bounds. But the fact of the matter is the scalar curl at all the points inside of this region R sort of accumulate to tell us how different the line integrals of these two paths will be. So we'll do some more examples of this when I see you next in class.